My name is Victor, and welcome back to another ALINT-PRO tutorial. In this video, we will discuss a few variations on the simplest kinds of synchronizer circuits that ALINT-PRO supports. Now, for any two asynchronous systems to communicate, you need some sort of synchronization scheme. Now, what we're going to do is we're going to go head over to the CDC examples, specifically the CDC Synchronizers demo, and we can go ahead and open that up. And you'll notice we have a list of 14 different projects that are going to contain 14 synchronizers that will be gone over through the course of a few different videos. In this video, we'll be going over 5 of them. There's also a readme.txt that contains a little bit of information on each of the individual synchronizers, as well as some violations you'll get for each synchronizer. So, if you want, you can follow along with this, but that's not necessary. Now, again, before running through any of the demos, ensure that you right-click on your workspace and hit Clean, so that you can clean every single one of those projects, just in case. Clear that out. And finally, before we begin, I want to open up the Policy Editor. So what I can go to is Tools, Preferences, and then we'll open up this window. We can go to Policy, and then we can go ahead and take a look at all the policies that we have currently active. In particular, I want to focus on the ALDEX CDC policies. So here, what I want to look at is I want to look at one particular policy that's going to allow us to use specific types of synchronizers. In particular, we can take a look at the ALDEX CDC 1.12, Use Recommended Synchronization Schemes. So if we open up this, we can take a look at the different types of synchronizers that will be allowed in your design. Here you'll notice that we have the ND flip-flop, the enable, forward enable, and then vendor, FIFO, and memory. So what that means is, whenever we use a synchronizer in our design that is not one of these listed, we're going to get a violation occur. Now, you can always switch these up and change them for whatever synchronizers you're going to be using in your design, if you know for a fact that they're going to work for your design. You can also add and take away synchronizers. So, with that out of the way, we can go ahead and close up this policy editor, ensure that when you are running these, you have all of these policies checked and enabled, and you would do that just by deselecting everything else, and then just selecting the ALDEX.cdc, and then you can save the policy editor by hitting Control-S, and that star goes away. So we can go ahead and close up our preferences, and then we'll be able to begin on our very first design. So the first design we'll be looking at is the ND flip-flop synchronizer here. Make sure that it is set as your active project, like so, by right-clicking and setting this as the active project. And then what we can do is we can open up these two source code files, and we can take a look at them and figure out what they intend to do. So taking a look at this .sv file, you'll notice we have two clocks, clock A and clock B, as well as an input D-in and an output D-out. What it looks like we have is it looks like we have 3 D flip-flops. So we have one reading in from the input D-in in the clock A domain into a signal called data, and then in the clock B domain, we're reading in that data signal into meta, and then reading meta into stable. And finally, that stable output is assigned to D-out. So we should expect 3 D flip-flops chained together, one with clock A as its clock, and 2 of them, the next 2, with clock B as its clock. And we can also take a look at the .adc file, just to take a look at our different clocks. So you'll notice here that we have clock A and clock B specified with different periods, and also specified as being asynchronous to each other. And then we also have our inputs and outputs specified with a delay with respect to their given clocks. So in the case of D-in, it's written with respect to clock A, and D-out with respect to clock B. So now that we've taken a look at those, what we can do is we can run our CDC analysis just by double-clicking on here, and we'll go through these stages all the way up until we finish with the structural CDC and RDC. And once that's done, now we can go ahead and open up the RTL schematic view. So here in the RTL view, you'll notice we see exactly what we saw before, or exactly what we predicted before. We have 3 D flip-flops all chained together in series. And for the first one, the data flip-flop, we have the data coming in and being sampled by this in the clock A domain. And the output of this is feeding into the meta register, which is clocked in the clock B domain, which also is clocking the stable register. And these two here form what we would call our 2D flip-flop synchronizer, Or in general, for multiple of these types of registers being chained together, you'd call it the ND flip-flop synchronizer, and that's the name of this project here. Now, we're also going to take a look at a few of the other windows around the screen here. Starting with the CDC viewer, you'll notice that we have our two domains listed, one for clock A and one for clock B. So, starting with the first, we have domain 1, and this lists the clocks for that domain, in particular clock A, and it also lists the crossings to and from that domain. In particular here, though, there's only a crossing coming from or coming out of domain 1, and it's going into domain 2. Specifically, that's this crossing from the data to the meta D flip-flops, from Q to D. And specifically, this is synchronized by the ND flip-flop synchronizer, or in this case, the 2D flip-flop synchronizer. And if we were to analyze domain 2, it would actually contain exactly the same information, just written a little bit differently. It's written as the crossings coming into domain 2 from domain 1, and then it lists the exact same crossing, also synchronized by the ND flip-flop synchronizer. We can also take a look at the clocks and resets viewer. So here we'll see our constrained clocks, clock A and clock B, at different speeds, as well as the RDC viewer, which also lists the clocks, but doesn't list any resets because there aren't any in this design. And we'll also notice that there are no violations here, because earlier in the policy editor, we saw that the ND flip-flop synchronizer was an allowable synchronizer for our particular design. And so lastly, we're going to move on to this view here, which is the CDC schematic view, the CDC schematic window. And we're going to go ahead and expand this domain over here on the right. You can also expand the domain on the left, but there isn't any particular useful information in this. What I want to take a look at is over on the right-hand side, this receiving domain. In particular, you'll notice that we're looking at the fact that this is an ND flip-flop synchronizer and that the tool recognizes it as such. Also, you could see that over in the CDC viewer tab. But here you'll notice we have this domain transmitting data over to the receiving domain, and it is being synchronized by this ND flip-flop synchronizer, and now we have that receiving point, the output of that synchronizer. So, now that we've gone through all those windows, we can go ahead and close them up and get ready for our second design. So our second design here is going to be the wide ND flip-flop synchronizer. So I'll go ahead and set that as my active project, and then begin by opening up each of these two files. And again, we can take a look at exactly what we're doing here, but you'll notice it's almost identical to the previous .sv file, with the main difference being that each of our signals, the input, the output, and the intermediary signals, are all 4 bits wide instead of just a single bit signal. And that is actually the reason why it's called the wide ND flip-flop synchronizer. And again, we can take a look at the .adc file, and you'll notice that the clock A and clock B, exactly the same parameters, same asynchronous groups, and you'll notice that D and ND have the same delays with respect to those clock domains. So, with that out of the way, we can again open up the RTL view by first going to the CDC analysis and running that. And so once this is finished, we'll go through the exact same flow, starting with the RTL view, looking at each of the windows, and then we can open up the CDC schematic window. So here's the RTL view, same as what we saw before, except these are multi-bit registers, or in this case 4-bit registers. And then we have DN feeding to data, data to meta, meta to stable, and that going out. Exactly the same setup as before. And we also can take a look at the CDC viewer over here. So when we open up domain 1, you'll notice that we have the crossings from domain 1 to domain 2, and we're listed as more than one crossing, because indeed there are more than one crossing, because there are multiple bits crossing this domain jump. And you'll notice that we have data bits 1 or 0, 1, 2, and 3, all crossing from data to meta. And you'll notice that these are mentioned as being synchronized by the wide ND flip-flop synchronizer. And we can also see the exact same information from this perspective of domain 2, crossings to domain 2 from domain 1, and then we have those are also synchronized by the wide D flip-flop synchronizer. We can again look at the clocks and resets viewer, and we'll notice we see the same 2 clocks. Same thing for the RDC view, and there's one minor difference in the violation viewer. Namely, we'll notice that we are not supposed to use the ND-flip-flop synchronizer for multi-bit data. So, if this violation or any other violation pops up while you are in the use of any of your particular synchronizers, you can inspect the policy over here in the policy editor, or alternatively, you can show the rule description in case you're curious as to why this particular violation has occurred and why it's important. In this case, if you read through the description, you would see that this type of synchronization could lead to data incoherence with different settling times and such. And because of that, it's not the recommended synchronizer for multi-bit data. Typically, you'd use something like an enable synchronizer or a mux synchronizer. So, in this case, we see that we have a violation for this type of wide ND flip-flop synchronizer, but it is indeed recognized, and we can verify that both by looking at the CDC viewer, but also looking at the CDC schematic window. So again, we can open up domain 2, and we can expand the view, and then we can go ahead and take a look at exactly what we see inside of here. And I'll go ahead and expand domain 1 because why not? So expand that, zoom out, and so we see exactly the same information as before, almost identical. The only difference here is that it's written as two 4-bit registers instead of just 1-bit registers. But exactly the same idea, and we do indeed still have the ND flip-flop synchronizer. And so with that, we can go ahead and close up all of these tabs, and then we can move on to our third design. So our third design for this video is going to be the ND flip-flop SRL Synchronizer. So we can go ahead and set that as the active project, and then we can go ahead and open it up. So taking a look at the contents, we can first start with the .sv file, and this is going to be a little bit different from the original project, the ND flip-flop synchronizer, but it's based off the exact same idea, just presented in a slightly different way. So here, again, we still have the same first D flip-flop, the flip-flop that is sampling from clock A, the domain of clock A, sampling DN to the data output, and then that output is being fed into the clock B domain. But instead of just being fed through two chained D flip-flops, we have this setup here where we have what looks to be a shift register, because we have the data being at the bottommost position, and then all of the bottommost bits of the shift register being shifted over 1 into the topmost bits of the shift register. However, the shift register is just a bunch of sequential or in series or chained D flip-flops. And then finally, the topmost bit of the output of that shift register is our output here. So in fact, this design is identical to the other ones with two differences. The first being that we have multiple registers doing our synchronization instead of just 2. In this case, because the SRL register is 5 bits wide, this is going to be a 5 ND flip-flop synchronizer, as opposed to the last example, which was a 2 ND flip-flop synchronizer. The second difference is that the way that we've written the HDL is slightly different, because it implies a shift register. And so the ALINT-PRO tool is going to recognize the fact that we've written it that way, and it's going to interpret it as a shift register ND flip-flop synchronizer, rather than just a normal one. And we can also take a look at the test.adc file, and you'll notice that it's exactly the same information here. We have clock A and clock B, same deal, both same periods as in the previous examples, both are asynchronous, D in and D out, both delayed with respect to their individual clock domains. Moving on to the CDC viewer, we're going to want to, actually before we do that, go ahead and compile this using the CDC analysis. And after we do that, we can open up the RTL view. All right, so it's finished up. We can open up the RTL view, and we can take a look and see exactly what we described before with the .sv file. We see the same input register data reading in DN with respect to clock A's domain, and then that input goes to the input of the one of the inputs of the shift register, and the other 4 inputs are fed by the bottom 4 bits. Whereas this goes into the bottom 0th bit, these bottom 4 bits go into the top 4 bits. And this is designated within clock B's clock domain. And then we have the topmost bit of the output, bit 4, being output as D out. And again, we can take a look at the CDC viewer to look at the information for the domain crossing. Specifically, we can open up the first domain, crossings from domain 1 to domain 2, and then we can take a look at the crossing of data to this SRL register. And you'll notice that the tool recognizes we are synchronizing using an ND flip-flop shift register synchronizer. And we could also look at it from the point of view of clock domain 2, but it's the exact same information, just written slightly differently. We can also look at the clocks and resets viewer. Again, it's just showing that we have clock A and clock B. Same thing for the reset, the RDC viewer. We have just our clocks. It doesn't show any of our resets. And we can finally take a look at the violation viewer, which again is going to be showing us a violation, but different from last time, because this one is violation 1.12, which is the violation we brought up at the very beginning, namely that we have to use recommended synchronizer schemes. So again, if we were to show this in the policy editor, we'd note that this type of synchronizer is not listed or is not in our list of allowable synchronizers. It's not any of these. Again, you could change this list or add or take away from that list so that in the case that your design asks for a shift ND flip-flop synchronizer, then you can enable it and you won't get any violations. Closing that policy tab, we can also take a look at the very last tab, namely the CDC schematic window. And again, we can go ahead and expand both of these and zoom out to show their full breadth. And then we can see the crossing. And again, we can see that the name is the NDFF SRL Synchronizer, or the Shift Synchronizer. And it's the exact same information as shown in the previous ones, where the tool recognizes what kind of synchronizer we're working with. All right, so now we can go ahead and close all of these up and move on to the fourth synchronizer of this video. So the fourth design we'll be looking at is going to be the half-cycle ND flip-flop synchronizer. So what we can do, again, set this as our active project, and then we can go ahead and take a look at our different files here. And while I'm looking at this, I'm going to go ahead and compile the CDC analysis. So what we can see is, again, we still have clock A and clock B, D in and D out. And we do indeed have clock A being the clock domain where D in gets passed to data. And we do indeed have the exact same idea for clock B passing data to meta. So both of these two D flip-flops here are exactly identical to the previous designs we've seen. But the main difference here, and the reason why it's called the half-cycle ND flip-flop synchronizer, is because of this third register here. So here you'll notice that it's still clocked in clock B's domain, but it's not with the positive edge, it's with the negative edge of the clock. And so what this means is that this synchronizer is able to work faster than the original ones, because it only takes half of a cycle to go from one register to the next. Or in other words, it takes a full cycle to go through both of these two registers. And so it takes half of the time. So the latency is decreased, and if that's important for your design, then this is something that you can possibly use. So with that in mind, then that stable gets fed to D out, as we've seen in the previous examples. And we can also take a look at the test.adc, but again, nothing has really changed. Exact same periods, exact same clock groups, and the exact same delays for the inputs and the outputs. With that all out of the way, we can go ahead and again look at the RTL schematic view, and we see exactly the same picture we saw at the very beginning with the ND flip-flop synchronizer, with the one important difference that the clock B is being read on the negative edge of the clock here for this last D flip-flop, as denoted by this inverter bubble. But again, that's the only difference here. We can again take a look at the CDC viewer and open up the crossings from domain 1 to domain 2. And we'll notice that that crossing, as we've seen in the previous examples, is synchronized. But in this case, it's synchronized by the half-cycle ND flip-flop synchronizer. And that's denoted here. And we can also take a look at it from the perspective of domain 2. And again, it mentions that it's synchronized by the half-cycle. Clocks and resets viewer hasn't changed. It's still the same two clocks, same periods. Same thing for the RDC viewer. And the violation viewer here has two violations for us. The first is 1.12, the one we saw last time, where we're not using a recommended synchronizer. And so again, you could just edit the list and add this in the list if this is a synchronizer you are trying to use in your design. And then we have the second violation, which is that you only want to use a single edge of your clock in your design. So here that's 6.1.2, and you can also see that in the rule description viewer. And so here it just lists the reason why the violation has occurred, just to make the design less complex to analyze. That's the main reason why this violation is here. But again, sometimes you will ignore or waive these violations for your design. So, closing up the policy editor, we can take a look at the last window, which is here, the CDC schematic window. And again, we can go ahead and expand our view. Specifically, we're going to be taking a look at the right-hand side here. And you'll notice that the crossing from domain 1 to domain 2 is fed through these two D flip-flops, and the tool again recognizes this as a half-cycle synchronizer, rather than any of the other ones we've done so far. So, with that out of the way, we can go ahead and close out all of these tabs, and we can move on to the final synchronizer in this video. So, the last synchronizer that we'll be talking about in this video is going to be the reset synchronizer. So that's this one over here in this project. So we'll set it as the active project and open up the two files. So here you'll notice this is already a little bit different from the other projects. Namely, we have a clock input in just one of them, as well as an asynchronous reset input, and then we have the typical D in and D out. So this design is a little bit different because it's specifically made for synchronizing asynchronous reset signals. That's its entire purpose. And so it's a little bit of a weird concept, because why would you synchronize a purposefully asynchronous signal? And the main reason is just because if your reset signal deasserts at the same time as an active clock edge asserts, you get metastability. And so you just have to make sure those two events don't occur right at the same time. That's the whole purpose of this synchronizer. So you'll notice here we begin with this block here, which details two different back-to-back D flip-flops, both of which have this asynchronous reset, which when active is actually going to set each of the bits. And otherwise, the first register is just reading in a 0, and then the second register is reading in the output of the prior register, presync. Finally, this output here, reset sync, or RST sync, gets output as the asynchronous reset for the D out value here. And so what occurs is D out is going to either be reset when reset sync is on, or it's going to read in the input data otherwise. And then we can also take a look at the .adc file. So you'll notice we have this clock with a period of 10 in its own asynchronous clock group. And then we have D in and D out both stated with respect to that clock, because they're actually in the same clock domain. And then we have to set a false path for our asynchronous reset, because it is asynchronous. And then we also have to create our external resets, just give them names so that the tool knows what they are. Specifically, we have ARST, which is an active high reset. So now that we have that out of the way, we can go ahead and head over to the Flow Manager and begin our CDC analysis. And once that's finished up, we'll begin by looking at the RTL schematic, because it's going to look a little bit different from the previous schematics that we've looked at so far. Excellent. So now that that's done, again, we're opening up the RTL view. So taking a look at the RTL view, we have a very similar idea to what we just took a look at with the .sv file. So we have two D flip-flops, both of which being controlled, or rather having their sets or resets being controlled by ARST. And the first has an input of 0. In this case, it's 0 pulled through a pull-down resistor. And then the output of that feeds the input of the this second register. All three of these registers here are working off the same clock CLK. And the main difference is that these two registers here are doing the work of creating the now synchronized reset signal. And that's this wire here, which if you were to hover over it, it lists as RST sync. And so now these two form our reset synchronizer. So we can go ahead and take a look at the CDC viewer to see exactly what the tool recognizes this type of synchronizer as. So we can look at the crossings from the asynchronous domain to domain 1, and it lists two different crossings here. That's going to be these two, which are both synchronized by the, reset synchronizer. And reset here is just short for reset synchronizer. And so each of these two signals are just these two wires here, so the reset presync and the reset sync. We can also, again, look at it from the perspective of domain 1, but it lists exactly the same information, just from the perspective of domain 1. And then we can also take a look at the clocks and resets viewer, because this has changed a little bit. Specifically, we can see that while clock is the only clock listed, we have ARST, which is the asynchronous reset. And of course, we could open this up and take a look at what the branches show, but not a whole lot of information here that I want to show for this video. So closing that up, we can look at the RDC viewer as well, again showing our one clock and our reset, but there are kind of two resets here. We have ARST, which is the reset for these, and then we have reset sync, which is the reset for D-out. This is why it lists two resets here, but one is derived from the other. So closing that up, we can also take a look at the violation viewer. So over here in the violation viewer, we can open up test.sv, and we can look at the reset sync module. And in particular, we have this violation here, 9.1, which just says we should have our reset generation logic in essentially a separate module. This isn't that hard of a violation to fix, but you can also open it up, show it in the rule description, just to read why you do this, just for our hierarchy, make your life a little bit easier. So we have two more views to take a look at. The first is going to be the CDC schematic window. In this window, we have our two domains, the asynchronous domain and the clock domain, which we can expand. And then we have the clock domain down here, which we can expand as well. So here, you'll notice that there isn't a whole lot going on, and that's because the real meat of what we want to see is going to be in the controls schematic viewer. So opening that up, we can do the exact same thing we just did. We're going to expand both of these. And so now that we've expanded them, we can see in full detail what it is that I wanted to show. In particular, we see the reset synchronizer source here, feeding into two different places. First, this is an asynchronous reset, and it's being fed and used as a reset in a design. But it's also being sampled and used to generate our synchronous reset. And it's generated via this reset synchronizer, which is shown here. And so this reset synchronizer, recognized by the tool, generates our synchronous reset, which here it's still listed as asynchronous reset, and that's just because, well, it still is asynchronous. We've just made sure that its deassertions do not line up at the same time as the assertions of our clock. But it's still asynchronous, and so we feed it to, we feed this signal as well as the original asynchronous reset over to whatever modules they're going to. In this case, we know what they are. It's just going to be the resets for these two and the reset for this register here. And so that's why it lists those two sources. So we've gone ahead and gone through each of the 5 first synchronizers in this video. So just to recap, we've gone over first the ND flip-flop synchronizer, the most basic one that's at the heart of almost every synchronization scheme. Then we went over the wide ND flip-flop synchronizer, the exact same thing, just a multi-bit signal. The SRL Synchronizer, same thing as the ND flip-flop, just instantiated and expressed in HDL as a shift register. The half-cycle ND flip-flop synchronizer to save a little bit of time, cut down on the latency. And finally, the reset synchronizer, the synchronization scheme specifically for reset signals. So that'll be it for this video. Thank you very much for watching.